All right, hi everyone. Everyone prepared for tomorrow? Tests are here. Let's see. So we're going to continue talking about probability. And let us recap what we saw up until now. Remember that we were talking about probability, and we were talking about sample spaces, where is the set of all outcomes that you can have from an experiment, okay? And actually you can have several ways to pose these outcomes. It depends on what kind of analysis you're doing. And we saw that the probability of something happening inside the sample point, the sample space, is 1, right? So probability of S is the probability of having outcome 1 or 2 or 3 or 4 or whatever. So with certainty something will have to happen inside the sample space, so the probability is 1, okay? We also saw that the probability of an event happening plus the probability of not happening that event must also be equal to 1. If you remember, we talked about the pregnancy test, right? What's the chance that I'm pregnant plus the chance that I'm not pregnant? This has to sum up to 1 because either I'm pregnant or I'm not pregnant, okay? We also saw that when we have an event that it's composed of different sample points, right? Let's say outcome 1 and outcome 4. The probability of this event is actually the sum of the individual probabilities. So the probability of outcome 1 plus the probability of outcome 4. Okay? So let's say that you have 7 outcomes. You have a list of 7 possible outcomes. So your sample space has 7 outcomes. And I'm only interested in a kind of composition of sample points, of outcomes. To do this, we just sum up the individual probabilities. Okay? This is what we saw. So I want to do an exercise so that we can recap everything. Let's work with this. Is it? So say we're doing an experiment where we are estimating we're forecasting the weather, and here's my sample space. I kind of set up a sample space because I'm interested in analyzing rain and clouds and just it, okay? So I'm setting up my sample space with all possible outcomes. One of the outcomes, the blue one, is no rain and no clouds. The second one, the purple one, is no rain but still having clouds. The green one is rain and no clouds. And the fourth one is rain and clouds. So it's like the culmination of these two variables that I'm kind of assessing, okay? Up until now, we didn't calculate any probability. I'm kind of giving you the probabilities because we're analyzing these properties and everything. We don't know how to calculate the probability, but I'm giving you, somebody did the calculation, and the probability of no rain and no clouds is 65%. The probability of no rain but still clouds, 15%. The probability of rain and no clouds, 10%, and the probability of rain and clouds, 10%. Okay? So somebody kind of assessed the data and kind of came up with these numbers. So here's the question. What's the probability of rain? What's the probability of raining? Well, you can think about this way. The probability of raining, so my event E is the event of rain. Okay? You can either kind of describe it with words, or you can set up like your set notation, in which you have to tell what sample points are of your interest. So if I'm assessing rain, what events in my sample space are of my interest? Is the blue one of my interest? Is the purple one? Is the green one? Yes, because it's raining, right? So actually, the event of rain can come from two different outcomes. Rain and no clouds, which is the green one, and rain and clouds, which is the red one. Okay? And so if I have this event that is a composition of points in my sample space, the probability is the sum of the individual probabilities. So I'm going to take the individual probabilities of the green point plus the individual probability of the red point. Okay? And then we can calculate this, meaning that this is 0.1 plus for the green, which is rain and no clouds, plus 0.1 for the red. So this is 0.2 or 20%. Okay? So we're just kind of recapping the last property. So if your event regards rain, and rain has two outcomes, just sum up the probability of the individual outcomes. Okay? Now let's calculate the other one, which is the probability of having a cloudy day. Well, so now my event is cloudy, or I can kind of pose it as my set. What sample points are of my interest? Is the blue one of my interest? No, because it's no clouds, right? Is purple of my interest? Yeah, so this point is no rain, but clouds. What else? Is the green one of my interest? No clouds, right? So, and the last one is the red one, which is rain and clouds. Meaning that the event of having a cloudy day can come from two different outcomes. And so if I'm going to calculate the probability, I just take and sum up the individual probabilities of no rain but clouds plus the individual probability of rain and clouds, and this will be 0.15 plus 0.1. So the purple part 0.15 plus the red part 0.1. This is 0.25 or 25%. Okay? Good? All right. So now we're going to see a new concept named mutually exclusive events. This is how we name it in this course, but actually there's another name, and you might have seen this. I guess so, because the other section said you did, of disjoint events, right? So in some of you are doing stats, and I think in stats you saw as disjoint sets or disjoint events, okay? So what's the concept of mutually exclusive events? Well, the concept is this, that two events can't happen at the same time. Okay, let me just get rid of this. This is from the other section, sorry. So they can't both happen at the same time because the intersection events are sets, right? So because of the intersection being impossible or being the null set, they never happen together, the probability of the intersection is 0. Okay? So E and F can't both happen. This intersection here is the null space, right? So this is the same as saying that the probability of the null space is 0, which is another property of probability. Okay? So let us think about examples of two events that are mutually exclusive. The most basic kinds of events that are mutually exclusive is when they are complements. So for example, if I'm doing a pregnancy test and I say I'm pregnant or I'm not pregnant. Okay, so if I call this event of pregnancy E and call the pregnancy complement of F, or E complement, it is impossible to have being pregnant and not pregnant at the same time. Okay? So this is the kind of events that are disjoint or they are mutually exclusive. Okay? Now this is it's a too easy example, pregnant and non-pregnant, right? There are situations that we have to reason through the problem to check if the events can happen or not at the same time. Okay? So let's work out an example of this. And the example is Amy, Becca, Colin, Daniel are going to sit around a table for dinner. A round table. What is the probability that Amy sits across from Colin and Becca and Daniel are sitting side by side? Okay, so let's stop there. I'm asking a probability of something happening, okay? And actually, I'm asking the probability of something and something happening, right? So I have you have to break down the language here into two events. The first event, which I'm calling E, is the event of Amy sitting down across Colin, okay? And the other event that I'm calling F, it's Becca and Daniel sitting side by side, okay? The question is, what's the probability that E happens and F happens? So I am exactly asking if to find this probability of both things happening together. So before we calculate, we don't know how to calculate probabilities still, right? But before calculating the intersection and go through calculate, we have to check if the intersection is, if it's possible for these events to happen at the same time, okay? So what we can do, and again, when we say sit across or around a table, we are talking about around. So we have to kind of close the circle, right? So let's think about this. If Amy chooses to sit here, okay, event E says that, well, event E is actually Amy sitting here and Colin sitting just across Amy, right? Now let's talk about event F. Event F is this. Event F is Becca and Daniel are sitting together or side by side. Well, if Daniel sits here and we are closing the loop, we're closing the circle, we're distributing around the table, I cannot have Becca sitting here, for example, because they're not seated around the table. What's the only option for Becca? Well, it's actually sitting across Daniel. Okay? So the event E, which is A sitting across C, and Becca and Daniel sitting together, they cannot ever happen at the same time. It's impossible. Okay? So if you think about the probability of these two things happening is the probability of the null space or the empty set, because this intersection is the empty set. There's no intersection between these two events, and this is 0. Okay? This is a disjoint or a mutually exclusive event. Example of mutually exclusive event. Okay? And what would be a possible sample space of this? I mean, when we're talking probabilities, we are interested in this E inter F, okay? But if you think about the sample space of this problem, the sample space is the collection of all possible outcomes, right? So actually, S, you can see there, S is the collection or the set of all the combinations of sitting 4 people around the table. And we know how to do it already, right? It's the circular permutation of sitting 4 people around the table. It's 3 factorial. Anyways, you don't need to, we're not solving, like we don't need the combinations. I'm just telling you that that's why we kind of, the importance of knowing how to count, because we will use it from now on. Okay, so we will kind of now start to calculate the probabilities. And to calculate the probabilities, we will have to know the number of things inside S, inside the sample space. Okay? Questions? Cool. All right. So to start calculating things, the concept of probability is the likelihood, right? Of like, it's mathematizing this sense of, or this feeling of likelihood. And we were seeing probabilities, and we know some properties, right? We know mutually exclusive events. We know that probabilities must sum up to 1. We know that complement events are also sum up to 1, pregnant or pregnant. We know all of these properties. We know if you're talking about an event that has multiple outcomes, you just sum the outcomes, the probability of the outcomes. But how can we come up with the number P of something, right? So we're going to first set up this calculation in what we call equiprobable sample spaces. So we have to be in a particular context where your sample space is known as equiprobable, okay? Then we can calculate probabilities. Other than that, we're not going to adventure there, okay? But, so what is the definition of equiprobable sample space? So here's the definition. When the sample points, or the outcomes of the experiment in the sample space are equally likely, they are called, the sample space is called equiprobable sample space. When the sample points are equally likely. No, I don't know what the situation is here. Sorry for that. I don't know what this is. Okay. So when the outcomes are equally likely, okay, so when the outcomes of the sample space are equally likely, you have an equiprobable sample space. I'll give you an example. Let's say we are ordering a pizza, okay? And I order a pizza with 8 slices of pizza. So I have slice A, B, C, D, E, F, G, H, okay? Let me ask you something. What do you think? Let's use intuition. Do I have, if I close my eyes and I go and pick a piece of the pizza, is the chance of getting piece A higher than the chance of getting piece F? No, right? If they have the same shape, the same weight, the same color, right? So if things are, if there's no physical constraint in thinking that things are biased, this is an equiprobable sample space. Okay, and then we can calculate the probability. We know how to do that. And this, let's see if our intuition is calibrated, but what's the probability of taking piece A of pizza? Who knows? Who wants to try? Yeah, 1/8. 1/8, okay? Well, why is that? Well, probability is a ratio, right? It happens 1 in 8 times, or you can think about this as being like a percentage of the pizza. But I'm going to prove to you why is 1/8, okay? Think about this. What's the probability of taking a pizza? What's the probability of the sample space? If I'm doing this experiment, I'm going there and taking one slice. What's the probability of having a pizza? 1%, right? It's 1, this is 100%, okay? So the probability of the sample space is 1. Now, what's the probability of the sample space composed of? The sample space is the event sample space is pizza A, B, C, D, E, F, G, and H. What's the probability of the sample space then? We can use that rule that we individually kind of break down or sum up the individual probabilities. P of F, P of E, P of H. Oops, E, F, G, H. Okay? Now, I'm telling you that this is equiprobable. So let's say that this number, that this probability is little p, right? And it has to be the same to everyone. Okay? So it's little p, because they are the same. This is equiprobable. 1, 2, 3, 4, 5, 6, 7, 8. Oops. So in the end of the day, I'm left with this, right? So 8 times the individual probabilities must account to 1. So if you solve this equation, you will get that P is 1/8. So let's stop a little bit and go through it again. My pizzas they're equiprobable. My slices are equiprobable. And in the end of the day, all the probabilities must sum to 1, right? So you would have 8 values of probabilities that are equal, having to sum to 1. So which is the participation of each little p? 1/8. Okay? So because of this rule, this is a consequence of being in an equiprobable space. You will always have like the number of the probability will always be the number of things you're interested in over the total. Okay? Just like the pizza. I'm interested in piece A. Well, it's 1 piece amongst 8 possibilities. Okay? And that's the rule of probability. It is what probability is as we know it, equiprobable sample space. So in the end of the day, to calculate a probability, we break into 2 counting problems. One counting problem is the number of outcomes we're interested in. In the case of the pizza, I'm saying 1 pizza, but we could have like much more elaborate and intricate problems. And the number of total possible outcomes is the number of things in your sample space, right? So you have to know how to count. In the case of the pizza, there are 8 probable things, 8 possible outcomes. But that's it. That's why we learn counting, because to calculate probabilities, we will have to use this concept of the number of things or the number of outcomes that interests me over the number of all the possible probabilities. And again, this only works if I'm in the equiprobable sample space. Okay? We cannot use this probability definition to calculate things in non-equiprobable sample space. I'll give you an example. Say that you have a bucket, and you're like in that lottery things or bingo. You have like this bucket. Here, like you have a button here that opens, and you have ball number 60, ball number 39. Okay? If you do these balls with the same weight, with the same size, the chances of you opening here and the ball getting 60 or 39 is the same. Okay? But now let's say that you do ball 39, but way heavier. Okay? Or even not way heavier. You can put just slightly heavier. Do you think that you have the same chance of drawing 60 or 39? Actually, the ball 39 will go down. It will be heavier. It will tend to go down. And you will have a biased system. It's not equiprobable anymore. This is how the people like cheat on these kinds of contests or lottery runs. They slightly put more paint in the ball and try to make the ball a little bit more heavy, for example. Another experiment that is not equiprobable. A biased coin, right? So you kind of sand a little bit the coin somewhere so that in the end of the day it's not equiprobable to have heads or tails. Okay? Well, how can we calculate the probability in that situation? Well, it depends, right? Then this consequence of the properties that you have 8 things or 2 things that are equally like probable, kind of you lose that, and it will depend. Like let's say that this ball is bigger and this ball is smaller. You will have to account for the volume that this guy is taking from your bucket. So you will have to kind of you can calculate the probability, but it's not that simple. Okay? Yeah.
Did you ever put a question like that on an exam?
Like of biased things? If they put a biased thing, we will give you the probability calculated already. Okay. All right. Questions? Good? Okay. So here is an exercise. It says like this: a psychologist is conducting a study on memory recall. She presents a list of 52 words to a group of participants and asks them to recall as many words as possible after a short delay. Okay. This would be like the basic experiment. From that 52 words, 4 of them are emotional words, like love, fear, whatever. And the other 48 are neutral words, like book, chair, stairs, pen, cup. If a participant recall 1 word at random from their memory, so this would be the psychologist experiment, right? She would say, okay, can you recall all these words, the many words as possible? But now I'm asking this: let's say that you want to analyze just one word. If a participant recalls one word at random, what is the probability that the word they recall is an emotional word? Right? So now I'm saying, okay, you listen all the 52 words, and I say, can you give me one? What's the probability of being emotional? First of all, let's start from the beginning. Is this an equiprobable sample space? If I said usually, and this works for the test too, if I don't say anything, you assume it's a equiprobable sample space. We will discuss, after we solve, we will discuss if it is or not, but with some nuance. But let's imagine that the 52 words have the same chance of coming up. Okay? So we have a probability for each word as p, little p. Okay? Exactly. 4 divided by 52. Why is that? Well, now that we know that this is an equiprobable sample space, I will use the definition of counting problems that we did. How many outcomes are of my interest? How many emotional words I have? 4, right? I have 4. How many possible words that the person can give me as an outcome? 52. So this is 4 over 52 or 1 over 13. And it makes sense if you think about an equiprobable sample space, you can think about this. If all the 52 words have to sum up to 1, each word has a probability of 1 over 52, each of the words. And you want 4 of them. So it's 4 over 52. Okay? Now, in the other section, they asked them, but how do you know that this is an equiprobable sample space? Well, this is one question psychologists, for example, ask themselves. This could be part, and it actually is, part of several studies on whether words that are emotional are more like, they stick more on people's memory or not. Maybe they trigger something, and people remember them more than, than other words. So we are assuming it's equiprobable, and this could be a science experiment where you kind of, okay, I know that in theory we would have 4 over 52 chance of remembering this word. And then you call 1,000 friends or 1,000 participants and you say, let's do this. You do the experiment for 1,000 times. And in the end of the day, like in average, this probability is not 4 over 52. It might be, it poses a question on whether this is an equiprobable sample space. And then the psychologist will hypothesize that because our brain kinds of this, so this is what happens. Okay, usually. I'm not sure if I can give you the answer if it is or not, but as the exercise, we are considering that it is. Okay? Questions about this? Good? All right. Now I will give you 1 minute, 1 minute and 37, so that you can try to work this example out. All right. Does anyone have a guess? Sorry? 3/5 or 60%. That's right. Okay. So let's see how we can do this. There are two ways of doing it. I'll go through both. So you have a sample space. Imagine that you have a bucket with U, V, W, X, Y. So have 1, 2, 3, 4, 5 elements in your sample space. They are all equiprobable, meaning that there's no bias towards each letter, any letter. And you have an event. You're interested in getting V or Y. So you're drawing something and you're interested in having V or Y. What's the probability of not having V or Y? So it just kind of, it's a little bit, it's not having that. So two ways of doing. If E is this, the first way is a little bit faster, but it doesn't matter. You can do both ways. E is this event, right? This is E. What is E complement? Here, right? So this is E and V. Oh, sorry. Not E and V. So E is V and Y. Sorry. So E is V and Y. So it's this. Okay? What's the rest? What's not V and Y? Well, it's the rest, right? It's U, W, and X. Okay? All right, so what's the probability of having U or W or X? Well, it's an equiprobable sample space. How much is what's the number of outcomes of my interest? 3. U, W, or X. Amongst how many possible? 5, right? So this is 3/5 or 60%. This is like I think it's the fastest way to kind of think of the problem. Like, what I'm interested in is 3 of the letters, which are not V and Y, amongst 5. That's the easiest way. The other way of calculating this is first calculate the probability of E, because it's kind of it's stated deliberately here, like it's visual. The probability of E is 2 letters over 5, right? And then we use the rule, the pregnancy rule, the complement rule, right? So which is the probability of an event plus the probability of not that event has to sum up to 1. So I have 2/5 plus whatever I'm trying to find is equal to 1. So if I have 2/5, how much do I have to sum up to get to 1? Well, you have to work out the equation, and it turns out to be 1 minus 2/5. You can work this out, which is 3/5. Okay? There's 2 ways that we can kind of solve the problem. One, you solve like directly with the counting problems, right? The interest and total number, interest in the numerator, total number of possibilities in the denominator. Or you can kind of calculate first the probability that it's in your face and work out what you need to sum up to get to 1. Okay? Questions about this problem? No? All right. Okay, so now is made up by 52 cards. You have this. So A's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. J, Queen and King, right? So this is you have this sequence of numbers. So you have 13 cards, and this can be 4 different suits. You have hearts, you have diamond, you have, I don't know how to draw it, but I'll try. How do you call it? Clubs and spades. Something, I don't know. Something like that. Okay? So we have 13, 13, 13, 13. Okay, so here's the question. Consider that I have one draw. I have a deck of cards here in my hand, and I say, Andrew, can you get one card? What's the probability of the event E, which is the card drawn is of hearts, spades, clubs, or diamonds? What's the probability of that? What's the probability of, within all these options, you get a card of hearts, a spades, a clubs, or a diamond? Like hearts or diamonds, or, yeah. 100%. Yes. So in the end of the day, who is E? Who is my event E? It's my sample space, right? So this is actually this, which is equal to 1. Okay? Good? Yeah.
Quick question. If you have like a question about this on the exam, are we gonna have a deck of cards with jokers or no?
No jokers. Just the cards. Yeah. The jokers would make things. I don't even know if there's different there are different jokers, right? Types of jokers, right? I don't know. Yeah. No, we will use the 52 kind of. All right. So the other question 2 is drawing. What's the chance? So my event is this. What's the chance of drawing a 20 of clubs? Sorry? A 20 of clubs? Yeah. Do we have a 20 of clubs or 20 of hearts or 20 of something? What's the chance that I get this? It's 0. I'm certain that I won't have this event happening. Okay? So that's the probability of 0. Now let's do another question. Question number 13. Again, we have only one draw, right? And the question is, I have 2 events, getting a hearts and getting a clubs. What's the probability of getting both at the same time? I have just one chance. What's the probability of getting both? I'm drawing one card, right? Yeah. 0. Why? Well, because I have only one chance. I have only, if I have a heart, I can't have a clubs. I don't have a card like, I don't have a 2 of hearts, clubs. You know? I don't have these kinds of things. They are mutually exclusive. If I have one, I cannot have the other. Okay? So if they're mutually exclusive, what happens with the intersection? The probability of having them at the same time, it's 0. Okay? It won't happen. I'm certain that this won't happen. Okay? Now, for the 4th question, what's the probability of drawing a 7? I'll give you like some time to think. Who knows? Any idea? Yep.
It'll be 4 divided by 2, which is 4/7.
Exactly. Yeah. Or 1/13, like if you simplify the fraction. So again, we have a deck of cards that is fair. I didn't say anything about the deck of cards. So you, in the test, you should do the same thing. When we don't say nothing, you will consider that you're dealing with the equiprobable sample space, and then you know how to calculate probabilities with the combinatorics kind of way. So you will have a numerator, which is the number of things of interest, over the denominator, which are number of things that you, possible things that you have. In this case, how many 7s we have? We have 1 7 here, 1 7 here, 1 7 here, 1 7 here, meaning that we have 4 7s in the deck of cards. 4. And with respect of all the possible things, which are 52 cards. And then you can kind of simplify this. If you divide by 4 in the numerator and denominator, you will have 1/13. Okay? Cool? All right. So we are now kind of, I'm giving you guys examples that are very simple, right? Like in terms, just so that we can have this feeling that probability is what you want over what you could possibly have. And having this intuition of things that can't happen at the same time. But now, like we will kind of build up on this and work towards more difficult questions where I will ask you, okay, I want to know what's the probability of, I don't know, like you have 14 people sitting around a table, but one cannot sit across the other. How many ways can Joe and Billy sit together? So you will have to set up like the probability. You will always seek for a number of things that I want over number of the things that I can have. And you will have to work out the combinatorics, the permutations, selections, groupings, and everything. So how many ways can people sit? Oh, it's n-1 factorial. How many ways I'm interested in? Oh, in this case, if I select, if Tina sits, then Becky sits, and then 1 times 1, and you will have to calculate the 2 counting problems to do the ratio. That's it. That's how we will calculate the probabilities. Okay? So we're very simple now, but we will build up to more kind of intricate problems. Okay. Let's continue this after. Like, it's just because it's kind of a new concept coming, and we will work this after. Let's work this on Tuesday. Okay? Thanks.